we're heading into some circle geometry, and what we're going to go through with our circle geometry theorems is kind of this sense of proof to start with. So in this first one, I'll spend a bit more time with you on proof and the essence of proof and what it's going to do, and then for the others there will be a video on each. And it's up to you though, how much you're going to watch those videos, if at all, to be honest, because you might just get the sense of it from the static images and you can make sense of that, and that's great. Or you might want to watch the videos and get a bit more. But for this first one, I think it's important that we get this richness and depth. So I think, the question is, are you ready? Okay. Well, you know what, I'm ready, so let's hit it, yeah. So the line drawn from the center. So as I said, I want to kind of go through this idea of proof and use this as an example. So we've got some sort of theorem here, and we're going to prove it. Now, you get a number of different ways of proving various theorems, and some are more elegant than others. So sometimes you'll see like the Pythagorean theorem, the theorem of Pythagoras, is, there are lots of different ways to prove it, and people continue to come up with new ways, or are interested by different ways. And it's not about, it's true. It's about how you're showing that. So in this one, we've got this theorem that says that the line drawn from the center of a circle perpendicular to a chord bisects the chord. In other words, what you're given is that you've got some sort of circle. It's got the center O, and if we draw a line down here, and it is at right angles, it's perpendicular to a chord, and a chord goes from one part of the circumference to another, and it forms a very straight line. You think one day I'll look at this straight line. For once, a good straight line. Yes, happy. Okay, so we've got our line. So if that's the case, then this line segment AM is equal to that line segment MB. So the yellow bits are what we're trying to prove. So I'm going to remove those. You go, okay, so with this proof, we're going to need to do a number of steps. And as I said, there could be a number of ways to do this. Now, I say there are a number of ways. The only thing kind of just maybe to bear in mind is, we're going to use this theorem. Let's do it like this. We're going to use this theorem to prove something else. And then that something else, we're going to prove something else. But now you can't use that last something else to prove this, because that's like circular logic, right? Yeah. But, it is important that order. You can't use A to prove B, B to prove C, and then C to prove A, because, if A were false, the whole thing would tumble down. So, and as I said, there are going to be different ways. So let's jump straight into it and just work through the idea of this proof. So for this, we're going to use congruency in the way that I'm going to show you how to prove this. So I'm going to create two triangles, and let's actually get into these kind of nice straight lines. I'm going to create these two triangles by constructing those two special lines, and they're special because they're both radii, right? So we need to capture that thinking. So we're going to say, let's construct radii OA and OB. So we're capturing it nicely here, up here, and then we're drawing it over here as well. Now, what the essence of our proof is going to be is this, that we're going to prove that these two triangles are congruent. What does congruent mean again? It means that they're kind of the same. They might have been reflected, or they might have moved around or been rotated, but those two triangles are the same. So what we're going to prove is that this triangle over here is congruent to this triangle over here. Because if they're congruent, then it means that all the sides are equal to all the other sides. In other words, this side AM is going to be equal to that side BM. Okay, so that's kind of the essence, and then, we'll go from there. So let's jump into it and say, okay, so to prove congruency, we generally use this kind of template in triangle something and triangle something else. We're going to show three things, and therefore we could sum up that those two triangles are congruent for some sort of reason. Now, I don't know, how well do you remember your 4 cases of congruency? Jot down the ones you remember and really push yourself. What are the 4 cases of congruency? Well, 4 cases are side, side, side. If you could show all three sides are equal to all three sides, like those three are equal to those three, obviously they're congruent. You've got side, angle, side. You've got, what else have we got? Angle, angle, side, which of course doesn't matter the order, so you might have known this as side, angle, angle. And the last one we've got is right angle, hypotenuse, side. Now, the kind of one variation of all of these things that you don't have, remember there's no angle side, side. Okay, so just note that when you've got your congruency cases. So let's show our three things. The order doesn't matter. I think maybe we've got OA equals OB. We've made a statement. In geometry, we need to write a reason. And our reason is that radii. Let's just get into this. Remember, statement, reason. Hopefully you were doing that when you're revising and getting back into this section. Okay, then we've got this side OM. Well, it's common. So you could either write OM is common or OM equals OM. Always feels a little bit bizarre to write that's the same. But somewhere you're kind of mentioning this word that it's common. And, we're thinking, which of these are we going to use? Well, we're not going to use side, side, side because we don't know anything about the third side. Angles, doesn't seem like we know much about angles at all except for this 90 degrees. So we're not going to use those. We're going to use right angle, hypotenuse, side. So the other part of the puzzle, I think it's just easier. Just write a 1 and a 2. So we can call that angle M1 and M2. And I'm going to say that for our last bit, M2, let's give myself space here, M2 equals M1 and equal to 90 degrees, and we were given that bit of information. Okay, so we haven't captured our triangles. In triangle, well, the left-hand triangle I'm just going to call OMA, OMA, and the other one I'm going to call OMB, OMB. So, all these things on the right relate to that triangle, I think makes sense. So therefore, the two triangles are congruent. Just remember the order of letters matters here. Now, this triangle wasn't too bad to see that it's just been reflected. So OMA is OMB. But kind of just think through how you're going to remember how to get the order of letters correct. Don't want to spend too much time, but, it has to, OM equals OM, MA equals MB, OA equals OB, and angle O is equal to angle O, so that angle is equal to that angle, etc. Okay, and our reason was right angle, hypotenuse, side. So therefore, it flows quite naturally, obviously, just it flows from this statement that AM equals BM, or AM equals MB, which is what we were required to prove. So therefore, AM equals BM, reason, well, because those two triangles are congruent, then they must be equal. So that's kind of one proof. As I said, there may be other proofs to show this, and as you go along, as we go further into this, there are definitely going to be more and more different ways of doing it, but there's generally some sort of construction that you're going to have to do, and then lay out your reasoning in a nice, orderly fashion. Okay, so that's kind of idea of proof. So for the next few, this one, if you want to see how to do it, my hint is draw these radii again, and you'll be able to show congruency, and therefore that each of these is 90 degrees, in other words, that it's perpendicular. But for now, just know that this is what we're going to use. And take note of the reason. Fortunately, these reasons are quite long-winded, so if we use this theorem, we have to use this reason. So there's the one that kind of feels like the other way around, converse in some ways, and maybe if you're given both those bits of information, that equals that, and this is 90 degrees, that this must go through the center. Center's got to be, say, there, or somewhere on this line. A useful bit of practical knowledge, by the way, if you're ever looking for the center of a circle, is to construct that and construct another one, and clearly so if that equals that, and that's 90 degrees, you can make them intersect and find the middle of a circle. As I say, useful. I've actually used that in everyday life, somewhere where it was vaguely useful. So there's our last one. So we're going to use those. Now there are 3 examples. we'll hit those on the next video. And yeah, you can enjoy the proofs in the other videos. So I think with that, we need to perhaps just get our music back up and running as we ease back out.